Okay, so let's first review some of the triangle congruence postulates and theorems that we've learned. So the first one was SSS. So here's the point. How do I know that SSS is a proof of congruence? If three corresponding sides of one triangle were congruent to three corresponding sides of another triangle, does that necessarily mean that both triangles are congruent to each other? So here's what I've got. I've got three sides, right? And this red line controls the red side of each triangle, or each potential triangle. Here's the blue side. This controls each of the blue corresponding sides of each triangle. And here's the green side, which controls the green side of each corresponding triangle. Here's the deal. I'm going to try to create two separate triangles, two triangles that are not congruent if all three sides are congruent. If I can do that, then SSS is not a proof of congruence. Right? In other words, if I can create two triangles that have three corresponding sides equal, but those two triangles are not the same, then SSS cannot be a proof of congruence. What I can do here is only rotate these in both of these. So what I'm going to try to do is I'm going to try to rotate these two triangles, these two sides of the triangles, so that the B's correspond with each other, that the B's overlap with each other. And let's see. There we go. Okay, now I'm going to try to do the same thing here. So in other words, let me see if I can join these two B's so that we make a triangle. I'm going to try to do this as closely as possible. Not quite. And I think this should do it pretty much. Okay, so the question is, are these two triangles the same? Do they have the same shape and the same size? Now, what I need to do is just move this down a little bit. It's not going to move. Okay, so the question is, are these the same? Well, yes, you can see that they are exactly the same. So SSS, I know, is a proof of congruence. How about SAS? In other words, here I've got two sides, the red side, the blue side, and the angle in between. Notice the red side, the red side, the red side, the blue side, and the angle in between, namely this angle over here. That's the angle in between, the included angle. If two sides of the included angle on one triangle are congruent to two sides and the included angle of the other triangle, are those two triangles congruent? In other words, the question is, can I make two separate triangles, two triangles that are not congruent to each other, if two sides and the included angle of one triangle are congruent to two sides and the included angle of another? All I can do is I can move this any way I want, but in order to create a triangle, I have to join the B's. And the same thing here. I've got to join the B's. Okay? If I wanted to, I can extend this red side on both triangles like this. But again, I need to join the B's in order to create a triangle. I need to join the B's. So the B's are joined. Now, are these two triangles congruent? Well, clearly, you can see that they are congruent. So side angle side is a proof of congruence. This is a review. So we have SSS and SAS. How about angle, angle, angle? Can I create two separate triangles that are different even though all the corresponding angles are equal? Now, here's the deal. We know that if two angles of one triangle are congruent to two corresponding angles of another triangle, the third angle must be congruent to each other because the sum of the interior angles of a triangle is 180 degrees. So if this was 30, for example, and this is 30, and this angle here was 20, and this was 20, well, 30 plus 20 is 50, which means this third angle must be 130 degrees. 130 plus 50 is 180. So can I create two triangles that have three angles congruent, three corresponding angles congruent, but yet the triangles are not congruent? Well, let's see. Remember, I can drag this as much as I want. Remember, these two angles are still congruent, and these two angles are still congruent, and this third angle must be equal to this third angle, right? And so the question is, are these two triangles congruent? Clearly they are not. So angle, angle, angle is not a proof of congruence. How about angle, side angle? In other words, if I have two angles and the included side, here are the two angles. Here's the other pair of angles. Two pairs of angles and the included side, namely AB in both cases. If they are congruent, if two angles and the included side of one triangle are congruent to two angles and the included side of another, is that a proof of congruence? If I can draw two separate triangles that are completely different, that do not have the same size or the same shape, then ASA is not a proof of congruence. All I can do here is extend these, right? This angle over here controls the left angle in both triangles. This angle over here controls the right angle in both triangles. Let's do something like that. Let's make it interesting. And let's do that. All I can do is extend these to create a triangle. So I'm going to extend these as much as I can. There we go. And all I can do is extend these. Remember, the two angles and the included side in each triangle must be congruent to each other. Can I create two separate triangles? Two triangles that are not congruent. And there we go. So now let's see. Is this congruent to this? Well, clearly they are congruent. So it looks like angle, angle, side is also a proof of congruence. Angle, angle, side is a proof of, angle, side, angle, angle, side, angle, angle, side, angle is a proof of congruence. Here's the angle, here's the side, here's the angle, here's the angle, here's the side, here's the angle. Angle, side, angle is a proof of congruence. Okay, so this should be down in your notes. Method 3 for proof of congruence. We had SSS, we had SAS, and now we have angle, side, angle. Take this down in your notes. This needs to be in your notes. Or you can go to the textbook where I will also have this theorem as well. So if you want to put your player on pause, take this down, hit play to resume, and we're going to do a proof together. Okay, let's take a look at this proof. It says, given KT bisects IKE, angle IKE, and angle ITE. In other words, line segment KT, this guy right over here, bisects two angles, IKE. In other words, it bisects this angle over here. Okay, so in other words, KT, line segment KT, bisects this angle, IKE. And it says it also bisects angle ITE. So it also bisects this angle over here, ITE. What I should do is just have the angles. I should just have the angle notation. So what we're saying is that KT bisects this angle over here, which is IKE, and it also bisects this angle over here, which is ITE. Well, remember, before we start putting pen to paper, we start marking things up. What does that mean? Well, it means that angle IKT and angle EKT are congruent to each other. Now, it also says that line segment KT bisects angle ITE. Well, what does that tell us? Well, it tells us that, let me get rid of this. It tells us that angle ITK is congruent to angle ETK. So it looks like both of these angles, both big angle K and big angle T, are being bisected, which means IKT and EKT are congruent to each other. These two angles are congruent to each other. And if you want, you can use this little hash mark in addition to the arc. And it means that ITK and ETK are also congruent to each other. Why? Because, remember, ITE is also being bisected by KT. So it means that these guys are equal to each other. Well, what else do I know? I know that KT is equal to itself. A line segment is equal to itself. So therefore, I can tell that triangle KIT, KIT, which is basically triangle 1, is congruent to triangle KET, which is triangle 2. And the reason is for angle, side, angle. Here's an angle. Here's the side. Here's an angle. Again, here's the angle, here's the side, and here's the angle. Two angles and the included side. What other triangle congruence proof do we want you to learn? That is this one. In other words, angle, angle, side, which says that if two pairs of corresponding angles and a non-included side are congruent to two corresponding angles and a non-included side of another triangle, the two triangles are congruent. So that theorem is called AAS, angle, angle, side. You'll notice that the side is not between the two angles, right? So in other words, if I call this ABC and I call this triangle DEF, you'll notice that AC is not between these two angles, angles B and C. And DF is not between angles F and E, right? DE is not included between angles E and F. AC is not included between angles C and B, and that is called the angle-angle side theorem. Namely, if two pairs of corresponding angles and a non-included side are congruent to two pairs of corresponding angles and a non-included side of another triangle, the two triangles are congruent. Let's take a look at an example. So, is triangle ABC congruent to triangle BDC by angle-angle side theorem? Justify your answer. Well, let's see what's given to us. It looks like they're telling us that angle A and angle D are congruent to each other. That's great. It's also telling us that BC is perpendicular to AD. You can tell that by that little square over there, which means, obviously, that this is also 90 degrees. What else do I know? Well, I know that BC is equal to itself by the reflexive property. Therefore, I can say that triangle ABC, which I will call triangle 1, is congruent to triangle BDC, which I will call triangle 2, by angle-angle side. Where is the angle-angle side? Where here's the angle, and here's the shared side. That is equal to this angle, this corresponding angle, and the shared side. So angle, angle, side, angle, angle, side. Again, the side that they both share is this side right over here, which is BC. I hope that helps. Please take this down in your notes or copy the notes from the textbook, and you should be in good shape for tomorrow.